Then this is section 10.1, the very end of it. I just had one last quick example to talk about, and today's lecture, dated May the 3rd, Monday, would mostly concern itself with 10.2 and 10.3, basically closing up shop on the two distributions, two sample sizes of the two distributions regarding either means with known or unknown standard deviations, or even two different proportions. Which is what many books lead off with. Now, this book is kind of backwards, and that leads off with the t distribution. I've never seen a book. I've taught out about 30 books, and I've never seen a book lead off with the t distribution before, because z is a little easier, and it just seems to be backwards to me. But let's get to the last example that I kind of ran out of time on. And yes, I do have more information. Yes, there'll be some book work I assign, and I'll have to dip into the DeVore book a little bit for a couple of things today. We will have the final sections will be 12.3, 4, 5, and 6. The beginning of chapter 12 is a very easy review, and there's a couple little follow-up topics in chapter 12, but that should round it out. I was hoping to get to chapter 11 because part of it is quite simple, but we just don't have enough time for that. In addition, we don't have time for matched pairs in 10.4, even though it's an interesting subject. But in this particular example, as we get to the main lecture, we have some data that you could input into the calculator, of course, and the professor at a large community college wants to determine whether there's a difference in the means of final exam scores between students who took the statistics course online and those who took it face-to-face. And we're still waiting to hear about fall. I actually asked about it. The hope is that we'll be face-to-face in the fall, but there's no guarantee. I also tutor at Moreno Valley College. They're definitely going back live. Chaffey expects to actually be, as far as the tutoring is concerned, still online in the fall. So getting mixed messages from different places. And of course, everybody wants to be face-to-face as much as possible. But that's, well, beyond my control. I just do whatever they say. Stay out of the politics. Meanwhile, I kind of have shrunk my screen. I wanted to increase it. Anyway, is this a test of two means or two proportions? I don't see any real proportions here. One could imagine this as being a percent of a grade, being 100, so I suppose one could try it that way, but that's not what we have here. We have a test of two means. Of course, they have the calculator steps, which we'll talk about. I'm going to click on the solution so we can kind of look ahead. Are the population standard deviations known or unknown? Well, we don't exactly have them on our fingertips. They are part of the data. And we don't have any kind of other set of numbers that say that sigma equals blah, 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 which does happen. Doesn't happen much, but can happen. Happened to me. What is the random variable? Well, in other words, what distribution do we use? As it suddenly kicks into the large mode. The t distribution, of course, and then for part D, what's the random variable? We're going to be looking at the difference of the means. The mean of one group minus the mean of the other group. And then we continue with what are the null and alternative hypotheses, got hidden a little bit, and write them in words and symbols. So yeah, either they're the same, and the means of the final exam scores are equal for both types of teaching, which is very pertinent for now. I don't know how they saw this coming. But the alternative hypothesis means the mean of the online class is less than the mean of the final exam scores for the face-to-face class, which is pretty much what most people have found most of the time. Left tail test, of course, is pointing to the left, and the alternative hypothesis that really does matter. After you type all the numbers in and do all the steps on the calculator, you find a very low p-value, which is going to show rarity no matter what your alpha is, basically. But what are they saying here? What's p-value? Do you reject or not reject the null hypothesis? This p-value is so small, it's going to be less than any alpha. Did they give us an alpha? I'm certain, yeah, the alpha is 0.05. So way less than 0.05. And we reject the null hypothesis. This is just too rare to be believable. This would only happen due to random chance 11 times out of 10,000, a similar set of events being at least this extreme as we've seen. This is pretty extreme, in other words. It could happen on its own, probably won't. We're not betting on that. So we're going to say we reject the null hypothesis, which means that we prefer the alternative, which means there really is a difference, and it's a one-sided difference. The mean of online is less than the face-to-face. So yeah, tell me about it. But we try to help out a little bit by replacing one test with the final if you want, or we do it automatically, et cetera, et cetera. So we're trying to help out a little bit. But anyway, that's the conclusion on that one. We're not going to cover Cohen standards for small, medium, large effect size. I've done that before, but it's been so long. It does seem to be a little bit obscure. It's just computational stuff, but I'm not going to go into that. Okay, so let's go into the next section, if it'll let me do that. Yes, it does. This is the same thing that we just did in 10.1, except it's with the z distribution, the distribution normal curve using the z variable, and known standard deviations, which can happen. They say it's not likely. That's true. It's not likely, but it's possible with well-established data to come across something like that. It's possible that one of them is known and one of them is not. I believe you go back to the t-distribution if you have any uncertainty on that. I'd have to look that up. It's been a while since I've seen a hybrid example, though. So anyway, we have the normal distribution, which is really the difference in the x bars, just like before, is based on what we're theoretically feeling that the actual mu1 minus mu2 is representing the difference of the x1 bar, x2 bar difference as well. And here's the standard error, and it involves the sigmas. This looks very similar to the t-distribution. Once again, we will cross out the handicap. The book may provide an example or two of that. I'm not interested in them. We'll always set them equal to each other. One doesn't have to beat another by 5 points or something like that. That can be handled. I'd rather just get to the basic examples so we can understand them. There's this example here. This example talks about with the independent groups, and the population standard deviation is known, because these are not dependent on each other. The mean lasting time of two competing floor waxes is supposed to be compared, and we do 20 floors, randomly assigned to test each wax. Both have normal distributions. They have to say that because n is a little on the small side, less than 30. They'd better say something about normality. And so the number of months that floor wax lasts was wax number 1. Fill in your blank with whatever your favorite floor wax is. Maybe another one you don't care for. 3 months comes from wax number 1. 2.9 months comes from wax number 2. That's about 3 days worth of difference. And yet the standard deviation is slightly higher for the lower number, which is a little unusual. So wax 1 is a tenth of a month more. Is that enough to show more effectiveness? Well, let's find out. This is a test of 2 independent groups, of course, all that stuff. And so we have our random variable, x1 bar minus x2 bar, to see what the difference was, which of course is 0.1. Very easy to say that. And thus, of course, these means in the null hypothesis are equal to each other. So please take the easy way out. Show me that you paid attention. Unless you do it correctly, yeah, points will be charged if you start steering off in the wrong way. In fact, it'll be tough to get even a third to half a credit if you start going the wrong way, as literally dozens or hundreds of my students have done in the past. I really reject this old-fashioned way of doing the null. It does actually help in certain rare cases, which we're not seeing. And if we did, then we could make a big fuss out of it. But in most cases, that's just not necessary. So anyway, I've said enough about that. I hope you take heed and just put the equal sign in for HO every single time. You have my permission to do that. Make it easy on yourself. What can I tell you? Okay, so we have the distribution. Here's the standard error, which we can calculate. And I believe I did that if I have my notes in front of me. Not getting the pen out yet or the text box out yet. But that was a 0.1092, so it's a pretty small standard deviation for this test, involving 20 apiece. Notice how the N1 and N2 are the same, they're both 20. We're mostly looking about the mu1 being greater than mu2. That's the important thing. It's a one-tail, right-tail test, and we have our sketch of the p-value. I always found that the sketches were very important in comparing z's, but we're not really doing that here. So the sketch, I still can ask for a sketch. I'm just not as thrilled by them as we were when we used to have to compare z's, which is still a major method of doing it. We just have pretty much almost bypassed that here. We may have referred to it once or so. But the p-value turns out to be along the 18% mark, which will, happens pretty commonly. That's going to beat practically any alpha that we could throw out there, and it does beat the 0.05. They've written it backwards, in my opinion. P-value about 0.18 is definitely larger than 0.05. That's the way you should look at it. Don't look at it backwards. Anyway, I'm not used to it that way. And anyway, p-value is large. This is not rare. You can just tell by looking at it. That's going to happen kind of a lot. And when it's not rare, HO loves that. Do not reject HO. We pretty much like HO, yet we're not going to accept it ever. That's very important to know. So at the 5% level, pretty much almost any level of significance from the sample data, we don't have enough evidence to show that the mean of time x1 lasts is longer. It's not really more effective, and you could almost tell that by looking. Sometimes it's just a matter of common sense. Does 0.1 of a month, 3 days, really matter that much? I don't think so. Now, if we had 2,000 floors done each time, maybe that could show a difference. With only 20 apiece, total of 40, we just don't have enough weight behind this. And that's just the way it goes. Okay, so we have of course, our difference was 0.1. There it is. And I'm not actually calculating the z, but they do it here inside the explanation on the calculator. Be sure you find the two-sample z-test. Two-sample z-test on stats and tests. You don't have to tell me stats and tests, but you should, tell me where you are on this somehow. Arrow over to stats, press enter, and then type in the data. You've got your sigmas, 0.33, 0.36, 3 for the first mean, 20 for N1, all the various data points. It's pretty easy to do that. And then, of course, pick the greater then for the HA. Notice they don't even ask you about HO. That says a lot right there. HO is always the same, pretty much. So anyway, press enter. Arrow down, the p-value shows up, and the test statistic was a very mild test statistic. When you have a z with a 0 on it, you're sitting in the center. HO loves the center. And in fact, this time it'd get the center and all of the left end too, because we weren't looking at the left end. Even though our twisted hypotheses seem like we are, we're not. I'm not really looking over there. We're looking for it to be more effective. Who cares about less effective? That's just not even relevant. I mean, it's part of the sphere that HO lives in, but yeah, why would you worry about that? And too many people do, I'm afraid. I'm just trying to warn you of all the times I've had to grade tests, and I scream my head off about this, and so many people just ignore me. And I dare say there'll be at least 5 people in this class that ignore and then because of it go in the wrong direction or botch up the stuff. And yes, you should expect to see a few hypothesis tests on this test. And this is a huge topic in this class. This is kind of where we're aiming. And so for me to ignore it would be absurd. So we will not be ignoring hypothesis testing. And whether you have to write it up formally or not, that's separate from that. But you do have to be able to go through the work, at least with a calculator. And they have a try it. I'm not really doing the try it's this time. Here we have this example, example 10.7. An interested citizen wanted to know if Democratic U.S. senators are older than Republican U.S. senators. And as of 2013, this is 8-year-old data now, the mean age of 30 randomly selected. Seems like they could have gotten everybody, but they didn't. They picked 30 at random Republican senators, and their age was 61 years, 247 days old. Let's just go to the decimal. And 61.675 years old. Standard deviation is 10. Mean age of 30, once again, randomly selected Democratic senators. I guess if you had a population, things get a little different. So they did have to pick a sample. Okay, that makes sense. Notice there's a 10-day difference in their mean ages. Wow, that looks really important, doesn't it? And that's 61.704. They both ran to 61.7. I think it's pretty obvious where this is going. You thought that the wax wasn't much different. Neither is this. And does it indicate that Democratic senators are older? Well, let's see. We had the Republican senators being just slightly younger than the Democratic senators. And, it would be interesting to get a population on this, I suppose. And as of a certain day, of course, you have to timestamp it on a particular day. And they are just a little bit older, 10 days worth. I don't think that's going to be important. I don't know about you. But let's see what we have here. Population standard deviations are unknown. And so we do have the stuff that we can get. Oh, actually, they are known. So this is wrong. So another mistake. Sorry. Yes, we've been given the standard deviations. Well, anyway, they're samples, I guess. Yeah, they're samples. But we're going to go ahead and use the sigma. Something I didn't want to get into, but yeah, we'll go ahead and use sigma here. But we're not going to mince words. We'll tell you that it's a sigma, or we'll say that something that's from a sample, something that's maybe not from a sample, that kind of thing. So they went in alphabetical order, one for Democrat, two for Republic, and then we have the different HOs, and I'm only going to look at the first part, and I'm going to say that in the beginning, mu1 is equal to mu2. Who cares about that garbage there? And then we're looking at the Democrats being older, and they are just a little bit older. Does that really add up to much? And by the way, since we've got the sum of the sample size is equal to 60, which is greater than 30, we use the normal approximation to the student's t-distribution. So actually we're going to use z here. And so yes, the z value will be used in this particular case. And they go through and they find that the distribution here, and they're just really looking at the standard error, and we're not formally computing z here, but that would be found in the denominator there, and yet the average difference is 0 as far as the null hypothesis and the alternative hypothesis basically are concerned. And then that number, I did actually calculate that to be 2.5, roughly 2.5 as far as the standard error is concerned. That's not too important. We did find an actual difference between the two, 0.029 years, not much. And when you run it through the calculator, we find a whoppingly large p-value, which is not drawn to scale. They should have drawn it much closer to the 50-50 mark. Yeah, it's about a 50-50 chance you're going to find something like this just due to random chance, because the difference is so slim, it basically isn't there. There's no real difference between the two. And if we got a full census, then we could say, oh yes, there is a difference, but it wouldn't be a very significant one. So anyway, p-value is way larger than alpha. It's not even close, pretty much 50% versus 5%. Do not reject HO. We love HO here. It's hard to imagine much larger than this large p-value here. HO says that the mu's are the same. Forget about that less than part. They're the same. There's not sufficient evidence to conclude that the mean age of Democratic senators is greater than the mean age of Republican senators. Well, duh. 10 days difference. Give me a break. Somebody really thought that was important. You better have several thousand senators for that to even be considered significant. And of course, we don't have that many senators. All right, so let's move along, and we've got the proportions. So what I need to do before I do this is go back, and here's a little bit of something I got to talk about a little bit. And finding the WebAssign homework, I picked around 4 per section. I couldn't find any good problems that didn't really involve confidence intervals. So I have to show you where the confidence intervals are. And then, oh, by the way, OpenStax doesn't talk about confidence intervals for this. How weird. Book finally doesn't do that. I've never seen a book like that before. So we've got one book that's way too advanced for many uses, and one book that's rudimentary and skipping a lot of basic things. They're very strong on calculator use, which is okay, but they're dropping the ball on certain things. So try to get these two books to match up, and I'm locked in on the WebAssign on the DeVore book. I can't switch that. So let's see if we can get to the other book. And yes, here we are. This is the confidence interval for what we just talked about for the Z, actually for the T distribution. That would be that one. And so let's see here. That's basically just replace it with the sigmas and you'd be good. I thought I had that queued up. I guess I didn't. Yeah, so here we have that. Right, so just simply substitute sigmas for the s's. And it would take too long for me to find exactly where in the book that is. I thought I had that queued up. I apologize for that. But anyway, the confidence interval would be to take the raw difference of the two numbers, apply the correct z value. Z is important, and then whether this is a misprint or whether they're just using some theoretical stuff, we would be using sigma. Sigma 1 squared, sigma 2 squared, also known as variances, and put them in. And this could be called N1 and N2 for the first population, second population. The DeVore book likes to use M and N. Every book has to be just a little bit different. That's yet another challenge teaching stats. And first time I've really done it seriously out of 2 books before, so this is a challenge for me. Anyway, use that in 1 or 2 of the problems in the WebAssign, and then we at least can tell you we could find it. And many of you can just find this on your own, of course. And I will also look for the follow-up on this for the 10.3 proportional one. We'll get that in just a bit. But meanwhile, we do have some examples to talk about in 10.3, comparing two independent population proportions. This is so important that many books now lead off with this subject. Classic cases, males versus females, men versus women, and to see what their differences are, whether it's political polling or any other topic. There are many, many situations where men and women are pretty much in lockstep, very little difference between their preferences in proportions, and sometimes there's huge differences, a gender gap, so to speak. So they have some of the conditions that we need to at least be aware of. Two independent samples are they're simple random samples. They're independent, and the number of successes is at least 5. The number of failures is at least 5. Otherwise, you'd have to go to a different distribution. We're not going to do that. And the population should be at least 10 or 20 times the size of the sample. So yeah, don't make the sample too large, or there gets to be a bias involved, which we do not want to do. And yet you could be oversampling, such as what we did with the senators. We took 30 out of around 50 for each party, and that's yeah, kind of could be oversampled if you kept doing that over and over. We will need a pooled proportion, an average proportion for this type of idea. And I have to say, practically every book I've ever used is better than the two I have here, and I feel like my hands are tied behind my back, and I can't believe they chose these books. But that's enough of that. I don't want to get too much trouble here. But anyway, this is adding the successes x and the successes b and dividing by the grand total of the n's. Well, however you call it, n1, n2, na, nb, that does not matter. The distribution does have 0 in the mean, and then we have what I call p times q, cares about 1 minus p, and then the reciprocals of the sample sizes. And that's one way to go, but the test statistic, the z-score, all the stuff the calculator basically does for you, and I'm not going to ask for special calculations or anything, not enough time in the semester for that. I will say that this second part of the numerator is always 0 every time. We're not going to put handicaps in, so I'm trying to cross that out with my cursor. Just ignore that part, just in case you are using this formula. And once again, we divide by that standard error. This is what goes in the denominator, PQ times the sum of the reciprocals of the sample sizes. All right, so let's see how a example would work. Example 10.8. And this one talks about two types of medication for hives being tested to see if there's a difference in the proportion of adult patient reactions. So they get more clear about what that means. 20 out of 200 adults given medication A had hives 30 minutes after taking the medication, and 12 of 200 adults given a different medication B had hives still 30 minutes after the medication. That's their criteria. Do you still have what they call hives 30 minutes after taking the medication? And we want to see if there's a major difference between the first medication A and the second medication B. So let's take a look at how the solution would be done. The problem asks for a difference in proportions. Making a test of two proportions is extremely common. This is something I just had to cover. This is of vital importance. And yes, of course it's on the final. Give me a break. Obviously this one's on the final. Well, you wouldn't know it's obvious, but I'm just telling you. So yes, we have our hypotheses, and this is a two-tailed test. Fortunately, everybody's on the same page on this one. So we set the proportions equal to each other in the null hypothesis, which I would always do anyway. Or if you want, put the difference equal to 0. That's actually a little bit more graphable. Actually, it is graphable. The other is technically not so much, but everybody understands what you mean. And you can pick either one of these. You don't have to list both. Pick one. I picked the easy one. Just is PA equal or is PA not equal? That's fine. Good enough. And you can do the other one if you want to. They did say is a difference. So is the same or is a difference is neutral, does not go greater or lesser. It's a two-tailed test. Very important to see that kind of thing. So we find the distribution for the test. Looks like we would need the pooled value. I'm not quite sure if your calculator does that. I can't recall right now. It probably does. But in case you need it, you would have to take the 20 out of 200 in medication A. You can almost see it in the fraction there. But this time we're adding 12 out of 200 for the medication B. And yeah, it does seem to be a slight difference. And it's very easy to calculate these, by the way. Medication A has a 10% effect, and medication B has a 6% effect. And because the sample sizes are exactly the same, the exact average of 10 and 6 is 8%. That's P, C. And then Q C would be 92%, where there's no real problem at all. So all these people got rid of their hives much faster than 30 minutes, or at least faster than 30 minutes. So here's the standard error, PQ, and then there's some of the reciprocals of the sample sizes. And of course, we've already talked about the 10%. I'd put the extra 0 here for emphasis, and then the 0.06. And we do, from all of this and your calculator, get a p-value that's kind of high. Anytime it's above 0.10, you know HO loves that. And then, yeah, that alpha won't even matter too much, but we're supposed to give you alpha. We will go under the supposition, though, that if the alpha is not given, it will be 0.05. Okay? So don't say I didn't tell you. We have brought that up before. So if you don't see 0.05, it's 0.05. If you do see any other alpha, go ahead and use that one as far as your criteria is concerned. And so they've done the sketch. It's a two-tail sketch, and they split the 14% into two groups of 7%, which is nice and pretty and all. And it's a nice thing. I could ask you to do it or verify on multiple choice which graph is correct or something like that. Well, anyway, the 14%, 0.1404 for the p-value, far bigger than the 0.01, and p-value much larger than alpha. And we don't reject HO. We like HO a lot. HO is saying, as we recall, that the difference in the proportions is 0. It's not enough to show a difference. Let's see. Do not reject HO. That's not enough evidence to conclude there's a difference in the proportions of adult patients who did not react up to 30 minutes to medication and medication B. So that just isn't enough of a deal. So yeah, p-value greater than a. Yeah, so we do have that kind of a thing. Yeah, it does look a little off, but I'll check on that. Have a try it. You can certainly do those. I'm not really spending the time to do the try-its this time. I may come back and do some of those. We do have a couple more examples on 10.3, and I'll also get you the confidence interval for calculations for WebAssign. We'll get to that in a little while. The research study here was conducted about gender differences in what's called sexting. The researcher believed that the proportion of girls involved in this is less than the proportion of boys, and that's what I would guess. But way back when, in 2010, ancient history, among a random sample of middle and high school students in a large school district in the southern U.S., summarized in Table 1010. Well, here's the table right here. So apparently males, 183 of 2,231 sent sexts, and females a little bit less, have roughly the same number surveyed. And I actually calculated those percentages and found that the males had an 8.2% rate of that, and the females had a 7.2% rate of doing that. A 1% difference. Is that enough? We do have large sample size here. Okay, this is a test of two population proportions, and they're talking about M and F for males and females. That's fine. And so we look at the difference of the two, and they are starting with females first, minus males. Of course, that gets you into a negative value, which is, that's the way it is. If you have a choice, I'd rather go for the largest one first, even if it's a two-tailed test. Just makes your number positive. Just a slightly easier deal. Plus, they did list the males first. But hey, they went in alphabetical order. That's fine. It actually does not matter. The answers will be the same. They'll just look a little different. But to me, they're exactly the same. So looking at these two hypotheses, and yes, they're using the equal sign. Congratulations. Very good of them to say the P's are about the same. But then they're saying that the females are less than the males as far as the sexting is concerned. So, and you could look at the differences relative to 0 if you'd like. The less than scenario says it's a left tail test the way they constructed it. Notice if you had put PM first and PF second, it would have been a right tail test. Either way, it's a one tail test. And we find the overall percentage between 7.2 and 8.2 does average out at about the midpoint there, 7.7% for P. And Q would be 0.923, just in case you need to type them in. I don't know if you would if you're following the calculator process. And we do have some calculator steps, which if I missed them, I apologize. We will look for that coming up. And but let's finish up this example. The calculator will tell you your p-value is 0.1045, and if our alpha had been a loose 0.10, which is kind of a looser standard, it would have still been larger. And of course, here's our proportions, roughly 7.2%, 8.2% for males, as we said earlier. And we are drifting towards the left end here. And we were comparing it versus an alpha. Where's the alpha? Did they give us one? 1%, 0.01. But we have a 0.10. Big difference there. And we did find, and this is a little bit confusing perhaps, but if you subtract these two numbers, the numerator of our test statistic would give us around a 1% difference, as I indicated before. Because they started with females first, it's a negative 0.01. And then they put it out to 4 decimals. Okay, fine. 0.0101 negative. And so that's the difference of the two. So they're saying different things. And then it looks almost exactly like the alpha, but that's completely coincidental. We are only looking at the p-value as comparison to alpha. And yes, 0.0145 is a lot larger than 0.01. So yeah, once again, we're headed towards the center. Don't reject HO. HO says they're about the same. And they really are about the same, despite the fact we had over 4,000 people in our samples. They really have not established much of a difference here. And although at a certain level of alpha, it would have been a close call, but not for the very strict level of alpha. They have to have this at the 1% level, which we only are going to accept type 1 errors 1% of the time. We just can't go with that. It just isn't solid enough evidence. And they certainly say it's not sufficient evidence to conclude that the proportion of girls sending sexts is less than the proportion of boys sending texts. They're about the same. So if you need to just summarize it in another way, you could say they're about the same. I wouldn't say the same. That's a little strong, but about the same is certainly true. Here's, of course, the calculator used. Let's talk about it. Once again, stats and tests, and then press to prop z test, to proportions z test. And this z because you know what they are, and this is just comes out in the wash for proportions. Provided you have at least 5 successes and at least 5 failures, you've satisfied the binomial conditions, and we will not have to worry about that. I'm not sure if your calculator will give you an alert if it's too low. It might, but anyway, arrow down and enter the various numbers. Here's the successes, Sometimes successes are not exactly successful in my opinion, but anyway, we have the first group and the second group, and yeah, we started with females. So remember, you have to establish which one you start with. If they're simply not equal to each other for a two-tailed test, you don't really care which one goes first. I would have just gone with the flow and picked whatever I saw first as males first, and it would have been a positive number. But they give you, of course, so once you do all the rest of it, get all the, x1, n1, x2, n2, sigma gets calculated by itself. You don't have to worry about that. This is the best part about proportions. You don't have to worry about it. It's done automatically, given the certain minimums you have. And then pick the less than, of course, because we did decide to put the females first and the males second. Press enter, and then calculate, press enter. P-value shows up. And even the z-value, which says a lot to me, that's a moderate z-value. It's negative because it went over towards the left end, as you can see on the graph. But that's not a very strong z-value. I mean, the weakest z-value we see it means anything is a 1.28. And that got close to that in the same way that the p-value 0.1045 is close to a 0.10. But we did not use that criteria. That's important to realize. But to be fair, sometimes in journals, people will simply report the p-value and let the reader decide what alpha they'd like to put in. And for things like a 0.03 or 0.07, that can be a different conclusion from different people, depending on what they want to, how they want to define their alpha, how strict they want to make it. Remember, 0.01 for alpha is quite strict. 0.10 is rather loose in comparison, and 0.05 is kind of the golden standard. It seems to be the best compromise for most situations. Here's another example, example 10.10. Researchers conducted a study of smartphone use amongst adults. Cell phone company claimed that the smartphones are more popular with white people, non-Hispanic, than with African Americans. That's an odd thing to think of. But anyway, the results of the survey indicate that of the 232 African American cell phone owners recently sampled, 5% have an iPhone. This may be older data. Of the 1,343 white cell phone users randomly sampled, 10% own an iPhone. So we're looking at the proportions more than the raw data. Sometimes you would have a choice in the positioning if you wanted to do them. But the advantage of the proportions is you don't have to have a preconceived standard deviation or a list of data. So proportions are generally easy to do. I would not, find 10% of 1343. I would not find 5% of 232 and find the difference in means or something. I just go with the proportions. It's just easier. So show the solution. Let's try this. This is a test of two population proportions, of course, and you can let W and A be the subscripts, PW, PA. And we're going to be looking for the difference of the two. And they did construct it so it was a positive difference, which is slightly easier. And the difference, now suddenly they come up with Android. Another mistake. Apologize for the mistake. It's the difference in the proportions of the, as far as I can tell, it's a mistake, in the different racial profiling here of the types of people using this kind of a phone. It's the iPhone, apparently not the Android. So we set them equal to each other as we always do in HO. And then we put a direction, whether it's 2 or 1. It's a right tail test because we put whites ahead, which seems to make sense if the data says 10% for whites and 5% for African Americans. We should get the pooled standard deviation. I could probably ask you for that just out of a course, even if this is actually a very simple formula, so you could do this. I could ask a question on this if I wanted to, but it's leaning towards the 10% because there's so many more white cell phone users sampled. It might have been more fair to pick closer to 50-50 on the two groups, but that gets into other things that we don't have time for, but they're still considering it to be acceptable. But it does work out to be about 9.3% that are using this type of phone, and Q is around 91%. And so we have our distribution with the normal distribution with 0 in the center, because we always kind of go with H0, not a surprise that 0 is involved in H sub 0. That's kind of obvious to me. But then standard error, which could be also used elsewhere, but the calculator does your work for you. And we have the approximate normal distribution. Certainly we have large sample sizes. We don't have to worry about that. Calculate the p-value using the normal distribution, and it's a very small p-value. It's 0.0077. This is not going to happen on its own very often. There's something going on here. And what's our alpha? 5%. It's way less than 0.05. Yeah. So we also, of course, had our proportions, which they finally get around to saying. I would have said this much earlier, personally. In fact, that's why I did it. It's pretty easy because they already had mentioned it in the preface there. 10% versus 5%. And anyway, p-value is way less than alpha. 0.0077 is less than 0.05. And then at the 5% level of significance from the sample data, there is sufficient evidence to conclude that a larger proportion of white cell phone users use iPhones than African Americans. And Androids had nothing to do with this, apparently. And once again, to review, using the calculator, which you could do, and you could fill me in on a little bit of what you're doing here. I always appreciate that. And what I don't like is when somebody never says a word about what they did. That just offends me. If you're largely telling me what you're doing, then I could overlook the occasional misstep, I guess. But if you never ever say what you're doing, that's not a good thing. You need to document your work. If you're looking for partial credit, that's how to get it, by the way. If you don't tell me anything, it's all or nothing. And then it won't even be all, because I'll have to think about docking you something. Everybody else is showing some work and you're not. You stand out, and not so much in a good way. So I'm just trying to say the obvious to most people. Anyway, press tab, go to test, go to the two proportion Z test, sometimes known as 6, I guess. Arrow down, enter the data in here for the white people using the phone, and then the white people total, and then 12 people who are African American using the phone out of the 232 total. And arrow down to P1 and pick the greater than. So setting up the hypothesis is very important. If you pick it incorrectly, then the rest of your data is just wrong. And so we find the p-value does not match the p-value up here, 0.0077, and they're saying, oh, suddenly it's 0.0092. One of them I'm sure is correct. I'm not quite sure which one. I didn't actually double check this one, and I certainly don't want to waste your time doing it now. So that could be an assignment for you to see which one's correct. But it turns out it's not going to matter too much because both of them are way less than 0.05, the level of significance. And the test statistic is z equals 2.33, which we're not comparing z's really here, but it would definitely work out to be greater than 2 point. Well, anyway, we're not going to worry about that. Let's go and take a look at the confidence interval. I need to try to show you that. Let me shrink this down and get over to the next one, which is section 9.4 out of the DeVore book. So I'll click on that and go to the confidence interval. Large sample confidence interval apparently is all they're going to give us. So let's take a look at that. And this is important too. This will show up in one of the WebAssign problems. And we take a look at the difference. To get a confidence interval for the difference in proportions, we first find out what the actual data says. Let's find out. You can put parentheses around this. You could say P1 minus P2 is a certain percentage, or decimal, of course. Put it in decimal form. There's a z-value that would go with certain confidence intervals, and we've talked about it. 1.96 is the 95 percenter. 2.575 or 2.576, depending on what book you read, is the 99 percenter, and then 1.645 is the 90 percenter. Those are the only three that I plan to give you. Then, of course, we have estimates for P1 already found over here. Subtract it from 1. Get your Q1 hat. They're putting hats on for the estimates, from the samples. We'll divide by the first population size, called M. In this case, call it N1 if you'd rather. I'd rather just be consistent, call it N1, but that's not what they did. Do the same thing with the second group. Get your P2 already found back here, and then easy to get Q2. 1 minus P is always equal to Q. And then I would call that N2, but they call it M and N, no big difference. And all four of these are supposed to be at least 10 according to this book. So different books have different criteria for this, and that would be something that you would probably get to use in the WebAssign homework. So what I need to do now is to try to find some reasonable, and sometimes that's very hard, reasonable homework in the WebAssign, which is our platform that we were given. I don't have any other choice, except to give you a few book problems, which I do plan to do. It does say that the book does, the yellow book does have lots of problems in it, and they have a wide variety of stuff, and that's good because I can pick out what I want. I can pick out some easy ones for sure to make sure you know how to do it, and then maybe a middle one or something. Don't really plan to pick any advanced problems, but if I have to go to the DeVore book, then I can't promise you that wouldn't be too tough. But I'm going to really try to avoid DeVore unless I really have a reason to go over there as far as the book problems are concerned. And of course, book problems are always optional. You don't have to turn them in. I'm not really accepting them. But I would definitely do them. A students will be definitely doing them, at least trying them. I'll try to make sure you've got an answer in the back if possible. Occasionally I have to pick an even problem or some problem that does not have answers, but I'll try to see if I can get something you can shoot for. And then, of course, if a problem really bothers you, because this is as close as I can get to a practice test that involves a big part of the final, be sure to email me or show up during my office hours. Wednesdays and Thursdays I have office hour. This is the last recorded lecture, and the schedule, as we said, for May 3rd. May 5th, May 10th, May 12th are all live, and then we'll be live for our final, which is May 17th, 4 o'clock to 6 o'clock. So be sure you've budgeted the time for that. I hope you not have to be at work at 5:30 or something like that. You should plan on using the full 2 hours, even if you don't happen to use it. I'm not trying to pick a 2-hour test here, but it will be longer than an hour 15, is what we had before. There'll be a definite cutoff time. I'm thinking strongly of having a definite cutoff time for you to submit your PDFs as well. I'm afraid too many people were taking advantage of that, submitting it half an hour late, and then the answers wouldn't even match, or they'd conveniently forget to put the answers on Blackboard. Remember, the policy is, unless it's like a box plot or something involving just a sketch, and those are rare, try to put the answer itself on Blackboard. I'm not expecting you to show work there. Show work on your PDF. Now, if you happen to have time to type it into the Blackboard, okay, good, but there's a lot of problems with that. And some people can do it quite well, especially in this class, but still, if you're submitting a PDF, and everybody should, it makes about a 30-point difference in your score for those few people that didn't turn in PDFs. Please do that, and then that's where you can show your work, and show your work for your multiple choice. I pledge to try to give you more partial credit on the multiple choice. I did very little of that this time. I just ran out of time. But with the final, I won't have that so much to worry about, and for the first time in a long time, maybe the first time ever, I'm taking the summer off, so then I'll be able to pour a little bit more effort into the finals and see how that turns out for everybody. And yes, we will replace your lowest midterm score. But there's a few people, about a third of the people, that their final isn't as good as the first two midterms. And so we'll just have it status quo according to the syllabus, as we mentioned before, and it'll be exactly as it says that way. Otherwise, the final will be roughly half of your grade as it replaces one of your scores. Say you didn't have your camera on one of the tests, that's an automatic 0, so then your final would take the place of that. And yes, I do plan to curve it, although with the homework scores coming into the picture, the curve tends to come up somewhat. I don't do a final curve, I just look at the total number of points. And obviously I'd love to aim for 90, 80, 70, 60, but it's going to slip a little bit down to there. My usual rule of thumb is like 85 for an A, 75 for a B, 65 and 55 for the D. Nobody wants a D. But it could slip a little lower than that. I just don't know how it's going to turn out. I've got a wide variety of students in this class. Some people are just doing quite well, and others are doing a little less well, and others are just barely hanging on. But hang on longer. We're almost done. And we are looking at the easier book much more than the DeVore book. But I did have to get you the confidence intervals for the last two. You'll notice in 10.1, we did not have any confidence intervals. I was lucky on the WebAssign there. Didn't want to find them, but there were none that I had to worry about for confidence intervals, where that was not the case in 10.2 and 10.3. So anyway, that's why I had to show you at least the confidence intervals to say, yes, we did cover them, even though they didn't happen to be in the OpenStax book. Okay, I guess I've talked long enough. We'll be back, of course, live the rest of the way, starting May 5, 4 o'clock to 5:15. We'll be here, and we'll be covering sections 12.3 and 12.4 on May the 5th, Cinco de Mayo. And then May 10, our last regular class day, we'll be covering 12.5 and 12.6. And then May 12 should be all review. And if there's a little bit of cleanup to finish up chapter 12, okay, I can stick it in there too. But it should be virtually a review day. So if you have questions, that's a good day to bring them up, and then your fellow classmates can join in as well. And that could be on the chat or just vocally dive in, interrupt me. You can't do this on a recorded lecture. I'll also send out the cloud links, although they're being kind of discouraged recently. I will definitely send out the cloud links for you because I've got into that pattern, and we'll continue to do that. Okay, well, it's going to be a hot day today as I record this on a Friday, and should be out by Saturday. And sure to send me the email if you have any concerns or questions, and we'll talk to you guys later. Bye-bye.